Welcome, everyone. Again, I am Joe Mahoney, which is the Connor Professor of Civil and Environmental Engineering, and it's really my great pleasure to introduce this first engineering lecture series for the year. The series is presented in partnership with the College of Engineering and the UW Alumni Association. We've really got two great speakers. Paula Hammond is the Senior Vice President and National Transportation Market Leader at Parsons Brinckerhoff. Prior to joining Parsons, Paula was our Washington State Secretary of Transportation. Greg is a professor, and he is our Department Chair of Civil Engineering here, Civil and Environmental Engineering. His research area is applied mechanics, computational methods, as applied to structures, geotechnical engineering and transportation infrastructure. At any rate, it's time for our speakers to get started. So Greg, welcome.
This is really fun. It's uncommon that we get a chance to talk about something like infrastructure. Infrastructure, by definition, tends to be invisible when it's doing its job well. And we take it so much for granted that it's very easy to just think, well, duh. The exciting stuff is info, nano, bio, and surely nothing is changing in the world of infrastructure. So I have 5 points I want to make, and you'll know a point because it'll be on a purple screen, all right? There won't be a test, right? We professors get used to having the idea that people have to pay attention because there's a test. I don't have that, but it is fun to say, oh, let's see if I can count to 5 as the purple slides go by. And one of the points will be that there's equally cool and interesting and I think forward-looking stuff going on in the world of infrastructure that there is in all these other disciplines that we're familiar with. So first of all, point 1. Like it says, infrastructure is critically important really at all scales, locally, regionally, nationally, and globally. This image is a fairly well-known one from National Geographic. If you haven't seen it before, they've actually got a whole website where you can go. It's like what's under New York City. So it's real fun if you haven't seen this before, go check it out. You can sort of navigate through, and they actually have a version of this figure that's to scale. And it turns out that deep water on the bottom is way, way down. You got to like scroll your screen a very long way. So why is it so important? I mean, that's an assertion. That's not the same as really demonstrating it. Ultimately, it provides the technological foundation for civilization. Often when freshmen or sophomores say, well, what is civil engineering? I say, well, it's the engineering that undergirds civilization. And what I mean by that is, you know, what do you need for civilization? You need shelter, you need water, you need transportation, and you need to take care of waste. You need communication, all the things that basically enable all the other things that we like to do as groups of people in cities, towns, etc. So basically, it's foundational for that. In fact, the word infrastructure, I didn't know this, I looked it up. I don't really know Latin, but infra is Latin for beneath or under. And so basically, you can think of infrastructure as the proverbial man behind the curtain who makes it all possible without being seen frequently. So fundamentally, if you look both kind of where we are now and into the future, if the planet's going to be livable, it's really a matter of making our cities livable. And I've got this interesting quote here. You can read it. We'll spend more and build more in the next century than we have in all the history before this. And it's interesting when we look back in history, we look how far we've come. It's equally interesting to kind of turn and look into the future and just think of the scale of what lies before us, both as a challenge and as an opportunity. Another kind of way of looking at the same thing, undoubtedly a lot of you have seen this kind of statistic. Somewhere around 2006, 2007, 2008, in that time frame, the percentage of the world's population that was living in rural areas dipped below the percentage who are in urban areas. And you can see that trend is going to continue. So really, the way we're going to be able to keep the planet, say, livable and running is that we're going to have to figure out how to make the cities we have and the cities of the future run efficiently and work for the people who are there. Now, this isn't to say that the world is going to be paved over and will be one big city, right? An equal important part of all of this is the way that the cities will interact and interface with the natural world as well. Okay, so point 2. Infrastructure is everywhere, even though, as I mentioned before, it's often invisible. And I just have a single slide on this one. This was taken from the American Society of Civil Engineers, ASCE, website about the report card. And so, how much infrastructure do you use before noon? And this thing is going to start really slowly because I guess it takes us a while to wake up in the morning. And then it'll accelerate. So you wake up in the morning, you flip the lights on, they come on. Well, of course they come on. What else would they do? You turn on the water, you make your coffee, which is both using energy, and where's all that fresh water come from? You're taking a shower, water goes down the drain? Of course it goes down the drain. Where else is it going to go? You brush your teeth, take a walk. Dams, of course there's dams there. They've always been there, haven't they? Schools, transit, public facilities, you drive on bridges, roads. We have rail here now you can ride on, right? More drinking water, more energy, transit. How does stuff show up in your mailbox? It just does, right? You go online, you order it, and it shows up. Or you go to the store, and it's just there. You see trucks driving around every now and then, but how could it be any other way, right? And so by the time we reach noon, and again, solid waste, it's always nice to talk about all the fun stuff we bring to cities, but we have to, take stuff away as well. And so really by noon, there's the happy family. Infrastructure has surrounded and enabled so much of what they've done, largely invisibly. Okay, third point. As we hear all the time, particularly in the US, our infrastructure needs renewal. And really, you could turn this into all bad news, which is, everything's going to fall apart and we'll all be in a big pit tomorrow, which there is some truth to the crumbling that literally is going on around us. But really, I think the word renewal also means we've got the opportunity and responsibility to go back and make things even better than they were before. It's sort of the old canard of, well, if it's not broken, don't fix it. That's not really how engineers think, right? Because we always think, who cares if it's broken or not? I think I can make it better, right? And that's really, I think, the attitude that we're going to need, because again, the challenges continue to change for us. So here's the report card that Joe mentioned. We actually got a C instead of a C plus on this, or C minus on this particular one. Now, the slide's wrong. No, it's not. I just got the data. And I computed the average myself. No. So, again, if I were sitting out in those seats, depending on my background, and I should also point out that infrastructure is inherently ecumenical. Yes, I'm in civil environmental engineering, and some of us have that kind of background, but at the end of the day, it touches so many different disciplines. We happen to be often the ones who integrate and put things together, but it's much broader than just one discipline. Nonetheless, if I was sitting out there, I'd say, isn't that a little bit, asking the ASCE to grade infrastructure, isn't that a little like having the foxes guard the hen house? Because obviously there's sort of a conflict of interest, right? Who would stand to profit or benefit if indeed the country tomorrow spent $3.2 trillion or whatever the number is I'll have at the end here that we need. So if I was out there, I'd be a little skeptical, and I respect that. So what I want to do is show just a little bit. I'm not going to really go through all these things in detail, but give some indication of where the substance is that certainly underlies this, even if, is that really a B minus or should it be a B, or, right? The details aren't as important as I think as the overall message. So what do the grades mean? And again, I'm not going to go through all these slides in detail, but you can see A means not only is it good now, it's good for the future, okay? It's sort of not something that simply is serviceable and it's been there for a while, but generally, it's very good for the future. Good says, well, it's okay for now. There's probably some stuff going on that we need to worry about, but basically it's safe, reliable, capacity's okay. That's B. And on we go, mediocre, poor, at risk, and failing, critical, unfit for purpose. And this is where I'll make this point later as well. When you're talking about infrastructure, what does it mean if you get an E or an F? Well, it's not like you just go home and your parents say, you know, what's up, you got to study harder, right? You actually have things that are really quite disastrous potentially, okay? So the costs of not doing stuff, again, aren't just that we say, well, you know, I wish I had better grades, but hey, I'm not a good student. No, the implications are more serious than that potentially. So that's kind of what the grades mean. Where do the grades come from? And again, just going to quickly run through some of the criteria that the ASCE uses. They look at capacity, condition, funding, future need, operation and maintenance, public safety, resilience. Resilience is actually one of these words that's becoming very important nowadays with infrastructure. And I'll have a little personal story about resilience, which is the idea of once something goes wrong, how long does it take the system to get back to normal functioning? And then, of course, innovation. Okay? And so then with each of these categories, they basically look at different areas and then try to apply and come up with grades. Now, I'm going to, again, just relatively quickly hit some of the highlights that what the ASCE has done for our state. So first of all, water and the environment. Water is hugely important, again, at all scales. In the history of human societies, right, the #1 public health breakthrough of all times was essentially handling wastewater efficiently. Okay? In fact, when I first met the dean of the School of Public Health, shook his hand, first thing he said to me, he said, civil engineering, #1 public health breakthrough of all time. It's like, well, thank you very much. I'm not actually a water guy, but I'll take credit. So anyway, there's water quality and water quantity. Both are hugely important, right? Quality is what's in the water, what are we putting in the water. Our ability to detect stuff always stays a little ahead of our ability to treat water. So, you know, there's no shortage of work there. And quantities, you know, where's it going to come from? How do we meet all the various needs between fish, people, power, et cetera? So very important. And for our state, oops, hit the right button, there we go. Some of the things the ASC has pointed out, again, just some statistics that you can scan through. Drinking water, we've got 9.8 billion infrastructure needs over the next 20 years. We got 49 hazardous waste sites. We got wastewater issues, et cetera. So this is some of the specific things for one of the areas that went into the Washington State report card. Transportation, I will defer to Paula. She will talk more about that in detail. But if you think transportation is just roads, this slide is supposed to also indicate, again, it's really multifaceted. Public facilities. This is a part of infrastructure that sometimes, again, we don't realize. And here's a picture of our fine campus. And parks and recreation, schools, again, it's not that hard to look at these things, apply these criteria, and just start summing stuff up. And that's where these numbers come from. And again, you could argue, oh, that person was biased. Maybe it should have been, you know, maybe instead of 6.3 billion, maybe it's only 5.5. But it is billions of dollars. I think that's pretty reliable. And then energy is another one of these things. And this is something where we as a state, without working very hard at present, do quite well, because it turns out we've got 74 gigawatt hours of renewable energy, largely hydro. Of course, we've got a lot of wind now too, but largely hydro. And that gives us a leg up in a lot of ways from the rest of the country. Okay, so the bottom line of the report card is 3.6 trillion. This is what the ASC says. Again, you can, that's not like 0.6000. Okay? But it probably is on that order of trillions if you really look at what we probably should be doing. And another interesting statistic, the way they frame it is to say it's about 28,000 per household that we will lose due to kind of the friction in the system, if you will, if we don't do anything between now and 2020. So I've got a little story about that. We had a water main break, right, near University Village not too long ago. And I actually have, don't panic. So this is what happened in my office, along with, this happened in 48 buildings on campus. Ready? It's actually the video. This is from my office. Because I didn't think my kids or my wife would believe me. So imagine on a campus this size, 48 buildings, the alarms are going off. From a resilience point of view, that's not supposed to happen, right? You don't expect 48 fires, okay? And it's just because the water pressure dropped. These things automatically went off. So without going into great detail, in our building, all these classes got canceled. Everybody's standing outside. I did a little calculation that for a class about 40 to 50 students, the tuition, the state support, and everything else, it's about $2,400 a class that is spent, if you will, on each session. I sometimes like to remind students of that. It's like, hey, you know, we're all in this together. A lot of money's being spent. Let's take it seriously. So if you multiply that times however many buildings on campus had to cancel class that day, that's money. It's lost. You say, well, you can make up the classes, but obviously you can't make them up without, again, other costs as well. So this is just one simple local example of how a 73-year-old water main, okay, beyond its life, broke and had all kinds of side effects. So this is just kind of in my building, right? And it was much wider effect. So this is an example of how you get real costs associated with stuff that needs to be replaced and hasn't been. So what do you do about it? It's two things, really. You need political will, fundamentally, okay, because everything costs money. But as I mentioned before, it's also a matter of technology development. We don't want to just rebuild the same systems, and we don't. We've learned quite a bit, and we can do things better each time around. So the next set of slides is, so what is about infrastructure engineering that's cool? Which really means, what do I think's cool about it, right? Because I'm making the talk. So just quickly, timescales. I've kind of got my phone here as a prop, right? How long does a phone have to live? Maybe 2 years, right? Depending on the terms of your contract, and whoop, then out it goes, and you get another one. That's not how infrastructure works, at least it better not, okay? And this is an example, right? Roman aqueducts, classic, thousands of years old, literally, and still in use in many parts of the world. The physical scales are huge, right? Grand Coulee Dam or the grid for the whole country, right? And even up into Canada. So the physical scales can be staggering if you really think about what we've built and what we need to keep functioning. The multipliers can be huge. This is highway vehicle miles in millions. That's millions, and it's millions over on the axis. So we're talking millions of millions, right? Trillions. That's a lot of miles. It also means if you could make a 1% effect on what happens during those miles, right? Huge payback, or the opposite, depending on if you make something better or worse. When you buy a phone, right, you might pay for a service contract in case you drop it or something, right? But in general, don't fold, spindle, mutilate, keep it 68 degrees. Infrastructure, we don't get to do that, right? We don't get to build a floating bridge and say, please store at 68. We have to deal with whatever natural hazards arise, be they earthquakes, winds, etc. Again, very interesting, unpredictable at the end of the day, what you might have to face. The consequences of failure, as I mentioned before, it's not just, dang, we didn't get that right. What's the universal solution to an electronic device? You shut it down and start it again, right? And that fixes almost everything. We don't have that safety net, right? When things come down, we can, in the worst case, kill people. So this is the Minnesota bridge collapse over on the right, and of course, everyone's favorite around here, the Skagit collapse. My sister was actually there on the bank watching, and she called me. My phone kept ringing, and I was at a Civil Engineering Student Honor Society meeting. So a room full of civil engineers, and finally I got to answer them. What's going on? My sister never calls me, and she's like, I'm standing on the side of the river, and the bridge fell down. I'm like, no, but it was. Oops, push the right button. There we go. The other thing is, virtually all our projects are one-offs. In fact, I chose this slide in particular because you'd think you already built a suspension bridge over that water. Just build another one, right? But technology changes. Even when it's so close to being the exact same job, it is never the same job. We don't get to build prototypes, test them in the lab, tune them. We don't get a beta release, right? In large-scale infrastructure, you got to get it right the first time, okay? With tons of uncertainty. Very challenging. Especially in the world we're living in now, the proverbial greenfield project where you just go out and there's nothing there and you build a city. There's some parts of the world where that's happening, but certainly not in most parts of the world anymore. We're more in the business of rebuilding. For example, when the Twin Towers fell in New York City, right, you got to build right on top of that. Someday, the I-5 bridge through the middle of Seattle is going to have to be fixed, replaced. How are you going to do that, right? It's fascinating. And I think when John Stanton talks, he'll talk about some of the interesting bridge replacement technologies that are currently out there in development. And another thing that you can't steer away from, so you're going to get a talk all about the tunnel. If I want to make a new phone, I might have to, get some FCC clearance or something like that. But at the end of the day, it's just me and the stockholders and whoever I can convince to give me money to do it. With most infrastructure, it's politics as well as technology. And so this, again, puts a very different flavor on the constraints and what we need to do to get things done. And of course, the tunnel is a classic case of the technology is far from trivial. It's very impressive, and there's new things that are going to happen in that project. But the political challenges, right, were much more daunting for many, many years. So infrastructure development impact, I don't have many slides here, but the moral of the story is infrastructure advances, and in many ways is advanced as much as the things that you more commonly think of. This is just two pictures from China I took, the Great Wall, an old technology, but still in use, for nothing else, for tourism, right? And then a high-speed train also in China. So again, just one slide. This is one of these things where if you look at the evolution of building technology, et cetera, it's really remarkable what can be built now. And I'm not saying what can be built should be built. That's another issue. But in particular, on the left there, when this slide was, or when this picture was created, it was under construction. But it's done now. And so there it is. That's a tall building. Look how tall it is. I did this for fun. This is actually pretty close to scale. That's about right. It's about still another several hundred meters taller than 4 Space Needles. Okay? Holy mackerel, right? You couldn't have built that 100 years ago, even if you had all the money and et cetera. Okay? So technology marches on in our discipline as much as other. And I could go on and on about that, but I won't because I don't have that much time. And this is something more from the past. And this is one of what I consider one of numerous success stories. What happens when everything happens right? When there's the political will, the technology, and things come together the right way. And so this is just the story of Lake Washington, which many of you are familiar with, and I'll do it relatively quickly. But it was just a fundamental case where on the lower part of the curve there, scientist W.T. Edmondson here at the university was noticing that the amount of phosphorus in the lake was going up. Very easy to plot, kind of one-dimensional thing. And it was proportional to the amount of sewage that was going into the lake as the population increased. The data up at the top, you got to note that up is down, okay? So that's the Secchi transparency is basically a white disk that you drop into the water, and how far down can you see it? And so when you could see down 4 meters, about 12 feet, that was pretty good visibility, but as time was going on, the visibility in mid-summers when this data is from, you could see that you're dropping down about 1 meter. That's not good. Okay? The lake was basically eutrophying, and it was going to be serious problems. So in 1958, the same year I was created, actually, Metro was created. And then over the next several years, we actually have people here who could tell you the story from the inside, much more exciting than I can. Basically, over the next five years or so, they began building the plants and raising the funds that was needed to basically start diverting the sewage. Okay, and you can see the precipitous drop there in the diversion of sewage. The phosphorus drops, and by about 68 or so, look what happens to the visibility. It actually got even better than it was before. And there's an interesting, again, I'm not a limnologist, I won't pretend to know, but talk to somebody who knows, and they can tell you why it actually even got better than it was before because of some microorganisms and stuff that were active. But to me, this is especially in this area, an incredible story of political will, technology, good engineering, and ongoing impact that helped everybody, right? It's not one of these things where I don't live on the lake, why should I pay for that, right? That doesn't get you very far. It's like we all benefit from having a clean Lake Washington. Let's make it happen. Okay, so the last set of slides here then, we're out on time. The future of infrastructure. So it just happens coincidentally, my daughter had us watch the latest Star Trek movie. And it's really interesting to watch science fiction movies to see what do people think the future is going to look like. And the pattern I've seen is all the Hollywood people think the main thing that's going to happen in the future is we won't need wheels anymore. Have you noticed that? All the vehicles float. And they have patients in the hospital and they're floating on the beds. That's all they got? Man. And I'm just sitting there going, why would you want to float when you're in a hospital bed? You might as well be on a wheel, right? Anyway, I'd feel safer, right? What if they have a power outage? So anyway, it's interesting to see what these visions of the future are. You know, this is obviously one of these gee whiz pictures. I'm going to be a little more down to earth, so to speak. Basically, what is it that drives change? The constraints change, the context change, and basically the bars raise. I've got a little, this is something that was developed in our department. One of these things, Green Roads, is one of these rating systems so that if a company or if an organization wants to say, we want to do better, it's a way in which people can quantify bigger circles around the costs of what they're doing, okay? So different criteria than they had in the past. And then the tools we have to address the challenges, materials, methods, technologies, kind of what any engineer would have to play with. The future's got to be efficient cities, and there are lots of ways we'll achieve this. Again, just very quickly, we throw a lot of stuff away that's valuable. So resource recovery is this idea that let's view our waste streams as actually resource streams, everything from water and sewage to other kinds of things that we throw away. Localized solutions. Probably the kinds of things that are going to work in Seattle won't be optimal for Phoenix and vice versa, okay? So I think there's going to be more localization of what works, and we'll move more towards multifunctional systems. Something like a green roof, right? A green roof is, yes, it's a roof, but it can do other things as well in terms of gathering rainwater, or even you can grow stuff up there if you get serious about it. And my penultimate, second last slide. In general, you know, you hear people talk about smart cities and these kinds of things. I like to think of it this way, that if, like people, the infrastructure itself in a distributed fashion gets intelligence and the ability to observe itself and other things going on around it, you can actually think of collaborative models for ways in which things that typically are independent, or maybe there's some controller that tries to make everything happen, you can move more towards a model with, say, distributed intelligence, sensing, observation, and decision making. And I think already some of this is happening. We're going to see more of it. One little example, some of you may be familiar with this particular thing, right? It's a thermometer, or a thermostat, excuse me. You stick it on your wall, hook it up to your furnace, and it learns. It learns how you use the house. It learns how you turn the temperature up and down, and before long, it just does it for you. So that's kind of a baby step along these lines of sort of intelligent infrastructure. What if this thing could also look at the weather tomorrow, right? That data's out there, and say, well, you know, it's going to be cold tomorrow. I better turn the heat up tonight, okay? And that's just one step beyond what I'm talking about, and you can imagine how if you start playing the combinatorics of that, you can come up with some pretty cool ideas of what we might be able to do in the future. And in a sense, we have the ability to do it now if we just decide it makes sense. Okay, so there's my 5 points. Infrastructure, critically important locally, regionally, nationally. Infrastructure's everywhere. We're sitting in a building, right? And we're using energy. And I'm using time. We're almost done. Unique challenges for infrastructure engineering. Technology has developed a pace of other engineered systems, whether we see it or not, and the future actually is in our hands. We can do all kinds of stuff when we set our minds to it, and so if you have opportunities to get involved in whatever way you see makes sense, please do. So with that, I will turn it over to Paula Hammond. She's the one on the left, in case you're wondering.
Thank you, Greg. Well, this was a great way for us to think about how to talk about infrastructure in general, and then, of course, what I know more about and have spent my 34 years working on is transportation infrastructure. You really can't start thinking about where we're trying to head in transportation unless you think about where we've been. So I'd like to talk a little bit about where we started. Some of us with gray hair in this room can think back in terms of decades in transportation and remember when maybe we weren't all that old, but we remember where we've started in this state. It wasn't very long ago, actually, when Washington State's highway system was made up of county roads, which really started as horse and buggy trails. And we had a lot of mud, and we were trying to bring in vehicles as a part of the transportation system. In the early 1900s, in fact, those county roads were starting to shape what we know as our state highway system today. You can see the yellow lines that were the state routes that were designated by the legislature and proposed state routes, and you can squint and see even the interstate system that we have today. And the year that I was created, in 1956, after quite a bit of planning in previous years, President Eisenhower signs the federal aid highway system, which really changed the shape of the national transportation role at the federal government role, as well as that interstate system that we see today. But between the early 1900s and 1956, the highway engineers and bridge builders were madly trying to create and connect the cities and communities that we had. Remember how much logging and timber was a part of our infrastructure and our economy. And it was really important to be able to get the goods to market and to connect the communities. From 1956, we spent a lot of time as a state building the kind of infrastructure. The rail lines were being built, the ports were developing, the airports, as well as the roads and the bridges to connect the state and connect our economies. We spent those years in not only building the interstate system, but we were fortunate when in the late 70s and early 80s, the federal government said, well, if you want to finish your interstate system, we'll give you 90% of the dollars to do that. So all of a sudden, Washington State decided that we had highways or freeways that weren't quite done, and everything looked like a freeway to us. And we were able to capture a lot of federal interstate, 90% federally paid dollars to build and complete the I-90 bridge, I-5, I-405, Interstate 82, and Interstate 205 down in the Vancouver area. All of those were built with a heavy, heavy support from the federal government. The rest of what happened between then and through the 90s really was where the legislature could find enough money to help support building and widening bridges, roads, etc. We were able to continue to work along that vein. We today, wait, let me go back because there's something I wanted to point out. Did anybody notice the bridge or the bus hanging? I wanted to stick that picture in because that was one of our icy days back, I think back in 2007 or 8, when that tour bus hung over the freeway. And it was just an example of how connected both the interstate system is to the city street system and the network. Everything stopped that day as that bus, if you remember, hung over the freeway. And it also reminded us during some of these ice storms and some of these floods and other things we had in 07, 08, 09, that if we don't talk to each other and connect and think about resiliency of the system to recover from those kinds of incidents, we're not doing our job. So a lot of work's gone into that kind of connection and coordination in the past. We aren't done building in our state. It's interesting as you look around the country and you talk to other DOTs or other communities, the East Coast is so built out right now, they can't imagine widening highways much. What they think about is how to move the rail. Amtrak on the northeast coast, or on the northeast corridor is very active. They try and live within the footprints they had. We have tried to catch up in the West because we've had a growing population and because we've had a lot of space or had space to build and widen our infrastructure and make it stronger for the future. We still have more to do. You can see the examples of the Columbia River crossing that has been planned but thwarted by the legislature just this year, and I'm sure that story's not over. We'll talk more about that. The North Spokane Corridor, a project that was planned for over 20 years, finally is being built over in Spokane that helps get the freight movement on US 395 off of the middle of Spokane's downtown and moves it onto a corridor that can help enable West Coast freight movement and goods movement. Ferry construction, some of you might remember in 2007 when I had to pull 4 ferry boats from service. They were over 80 years old and they were leaking. So how do you live with and support an aging infrastructure when you have people's lives in your hands? And how can we as a state not take care of the infrastructure and the services that we have? Fortunately, the legislature, when they raised revenue in 03 and 05, put forth money to build 4 new ferry boats. And those are, 2 are done and 2 more are under construction. Of course, we're going to hear more about the Alaskan Way Viaduct, but the tunnel that is being there not only is a great piece of infrastructure that replaces a very vulnerable, seismically vulnerable bridge, but it will change the shape of the Seattle waterfront, which then starts you thinking, how does infrastructure connect with communities and with the environment that we're in as well? You'll hear a lot of folks talk right now about the projects to the ports of Tacoma and Seattle, and these gateway projects are completing corridors that were long envisioned. The plans are in hand, and yet there isn't money to build and construct those corridors. But this is what you hear the legislature talking about now, and you may hear more about that as they come back together in January of next year. So we've been in an era of building, 100 years of building, strengthening, expanding, making the best kinds of engineering solutions work for transportation. But we're at a place now where we're seeing declining revenue. We're not able to use the gas taxes and the weights and fees that we get for transportation investments to the level we had. We have a growing population. And yet we don't necessarily want everything to be a highway or an expansion solution. So we're thinking differently about transportation. So where are we going? We have since about 2007 in our state Department of Transportation been thinking differently about whether the first and best solution is always to build. We know that it really isn't. Technology has evolved to the place now where we can look at the pavement, every inch of pavement we have, and ask ourselves if there isn't a better way to operate that system more efficiently. And a lot of the technology that you'll see today and that I'll talk about in a minute really helps us move people through those corridors better. The second issue that we think about when we have a transportation problem, and usually it's safety or congestion, is whether or not demand management can help us solve a part of that problem. These first 2 options are much cheaper than investing in more concrete and steel, and will serve us better as we think about the environmental impacts and other community interests. And then thirdly, always, you would think about adding capacity, but adding capacity strategically. And think about what's best, what's the strongest, most resilient kind of infrastructure we can build that's not too big and not too small, but I guess you'd say just right for the kind of communities that we're trying to have and the kinds of economic support for growth that we know we need to promote. So as we look here at some of the tools that have come our way over the years, and because we're so technologically adept in Washington State, it's been easy for us at the state level to think about using some of these tools to use the system as efficiently as possible. So no longer do we think that we just should widen everything, but why not put some of this technology to use? Using, as you can see there, the most rudimentary kind of demand management or efficiency is the incident response trucks. These have only been in place for about, I'd say 8 or 9 years, but having vehicles and people there to help clear an accident helps get rid of the congestion that's caused by an accident or some kind of an incident on the roadway, and will also result in safety benefits by not having accidents that are created in the backups. Usually once you have one accident, you're going to have 3 more as the congestion backs up for miles on end. Some of the signs you see here are incident response or the active traffic management, where we're now trying to regulate and monitor the speeds of traffic as you come up north, coming towards Boeing Field. And that will help slow down the platoon of cars to the pace where you don't then have that seesawing of stop and go, which causes traffic, takes longer for them to recover. Ramp meters, they've been around Puget Sound for quite a while, but they're very effective. Maybe not if you're on the city street trying to get on the freeway or on the interstate, but it does help with the free flow of the freeway traffic, and it helps smooth out the merges on the freeway. And so what that does for us and helps us think with the communities about is how best to regulate and monitor those ramp meters so that you don't cause such a mess in the neighborhoods, but you do help regulate and keep the freeway flowing better. And of course we have a picture of the hot lane. That's probably on 167, which, taking the high occupancy vehicle lanes now where there is available space, allowing single occupant drivers to buy their way in for a price, but does help make that lane more efficient and helps maximize the use of the freeway system, and helps the general purpose traffic ease up by having people who are willing to pay their way through. Those HOV lanes, or the hot lanes, aren't real money makers, but they're really helping us in the demand management arena, help smooth the traffic and get more throughput on the corridors as we go through. But one of the other things we're starting to see around Puget Sound is not just buses as the only option for multimodal transportation. Now with Sound Transit and the 4 other bus companies just on the east side of Puget Sound, we have light rail, commuter rail, we have the South Lake Union trolley. Microsoft now, because they felt the need to get their workers over to Redmond and into their facilities, have created their own bus company, the Connector. Some of the things that we have been thinking about in transportation as we talk about demand management is not that you either should get out of your car and get on a bus, but the options that people have for travel. Intercity passenger rail, Amtrak, we were fortunate to get a great grant from the federal government for $800 million a few years ago, and that was going to enable us to have a better, more reliable intercity passenger rail, 4 to 6 round trips to Portland from Seattle every day, 2 to the north to Vancouver, BC, but yet one more way for folks to get on a longer space, the ability to get between communities and between cities. I like the technology that we're seeing now in the parking arenas, where if you go to SeaTac to the airport or you go downtown, you can see that on a certain floor or in a certain parking lot, there's spaces available. No longer do you drive in and wander around. That kind of technology is available, it's here, we need to take more advantage of that, and those opportunities are there. This little pink mustache lift car is an example of the ride-sharing community that's building in the Seattle area, in the Puget Sound area, and other major cities around the country. And what it shows is that there are folks who will do just about anything not to have to drive alone on the freeway, or that they're willing to try some options that will help ease their commute. And all of this is good for the economy, because the less we're all driving by ourselves, the more our freight can get through and our corridors can work more efficiently. So one of the things I mentioned as we're thinking differently about how to take care of the demand and what to do about transportation in the future, we're also thinking that it's no longer just about the freeway or about the highway or the roadway, or it's not just a transportation issue. And Greg, he talked about this. We're now trying to figure out, in an era where we have growing communities and more dense communities and the need for us to be more efficient, how do we make decisions in this three-bubble kind of an arena, keeping, of course, our economic needs for our states and our communities at hand, but also thinking about the environment. We don't want to have or build infrastructure that treads heavily on the environment. Some of those decisions have been made in the past, and we're paying for that now, and trying to be careful about the impact of transportation and transportation services on the environment. But what about the social end, the community end? How does our transportation decision, as we weigh the right solution, work in concert in those three areas? And you can see the kinds of things that are considered, from air pollution and habitat loss and water quality and noise in the environmental area, the health of the communities, the cohesion, the livability in communities, and then the economic part, the part that helps our state thrive and will keep us stronger for the future, moving goods to and from the market, from the fields to the market, and keeping our economy strong and having businesses that want to come here and, come here and be a part of Washington State's economy. So what's happening with the money that we have? Why do people keep saying that we're out of money in transportation? I wanted to give you just a couple of slides to give you a snapshot of your 37.5 cent per gallon gas tax and where it is today. The 37.5 cent tax was added to in 2003 and 2005. 9.5 cents in 2005 and a nickel in 2003. That added to 14.5 cents. That was the push the legislature had that was to build 421 distinct capital improvement projects, bonded at 100%. Those projects are nearly complete. They're over 84, 85% complete. But knowing that that 14.5 cents of the 37.5 cents is bonded for the next 25 to 30 years, kind of means you have to put it out of your mind. You're going to pay for it now for the next 25 or so years. You're enjoying the benefits of the projects that have been built. All the barrels and cones you've seen in the last 10 years have been all about this last gas tax increase. 11 cents of our 37.5 cents goes to cities and counties to take care of their paving needs, their maintenance, their basic use of the roadway systems in cities and counties. And 4 cents goes to debt service from projects we built prior to 2003. So of the 37.5 cents per gallon that we pay for state gas tax at our pumps every day, we have 8 cents left, basically. Each year when there's a budget put together to maintain, preserve, keep safe, and operate the highway system, state highway system that we have today. And that includes the ferry system. When we lost the motor vehicle excise tax in 2001, the ferry system, being a marine highway, came back into the gas tax as a user of the basic gas tax for any additional operating subsidy that it might need. We have about a 70 to 75 cent or percent fare box recovery on the ferry system. So actually the users of the ferry system pay quite a bit of that trip. But the problem that you hear a lot about today is this 8 cents. You might hear this somewhere. And that's why ASCE has given us a failing grade, because we look at this and think that in the future we're going to have a real problem. The dollar is shrinking. Gas tax is flat, it's stable, it's pennies per gallon, it's not influenced by inflation. So since 2001, a dollar that we had there now is worth about 53 cents. It was a 47% decline because of the fact that through the 05, 06 era, we had a huge growth of inflation of materials and construction costs, and our money just isn't going as far as it used to. So we've got a gas tax and transportation revenue system that just doesn't keep pace with the needs on the transportation system or the costs that we're experiencing. And so it's a good reason why we're trying to be more efficient as a state, as a region, in the cities and counties, with the use of the money and with the use of the improvements and how we think about transportation futures. So you saw a little bit about this. This is another snapshot of ASCE's slide. And as I've worked with the other state DOTs and folks in transportation around the country, I've heard for years that they're already there. They've been in a very deep decline of investment. We in Washington State were very fortunate when the legislature passed those last two revenue packages, but those were spent on mostly new improvements. Very little preservation came out of that 14.5 cents that I talked about. So as we look to the future and we have new projects that are in place and benefiting the transportation system, we're worried about how the basic preservation of the system might look. So I've got some slides here that the only important part is the color. If you look at today's pavement conditions as an example, we have about 9% poor and very poor pavements in our state and 15% fair. We've moved, if you're familiar with the rural roads in our state, we've moved away from what we called full-depth asphalt overlays, which is what we tried to do pretty much throughout the system in the past. We're using a lot more BST, bituminous surface treatment, chip seals. We're starting to look at rural highways in the state, and we're saying, how many trucks, what percentage of trucks, what are the weights of the trucks on these roads? Can we get by with chip seals just to hold over the roadways? We've been in that practice now, and it's growing for about the last 4 years. So while our pavements are in pretty good shape, 75% good and very good, what we see is in the future, we don't have the money in the budgets or available because of this decline in purchasing power. Folks have been driving less. The cars that are hybrids now go 2 and 3 times the distance on a gallon of gas than they used to. And so all of a sudden, the revenue isn't coming in the way it used to. We look at what our available funding will do for us in the year 2023, so about 20 years out from now. And you would have about 44% fair and good, and the rest, well, 3%, 47% fair and good, and the rest would be in bad shape, which is the potholes that Greg showed. I think I saw that pothole on I-5 this morning when I came up, by the way. And so the other slide shows what the discussion of the proposed funding is. The story here is not exactly what percentage will be fair or good or bad or poor. The story is we're not taking care of our infrastructure in our state. While we were in the quest to build 421 projects, the legislature chose this time not to invest in preserving the basic asset that we have. And it's going to become a very big deal in our state. And while, yes, the bridge at the Skagit River fell down, it wasn't because it fell down because it was old. It fell down because it was an antiquated sized bridge and got hit and didn't have the kind of height and support structure that could sustain that kind of a whack from a bigger and heavier vehicle than what we've seen and what we're starting to see around the transportation system. So I declare that we're at a fork in the road. We know that there are investments that we need to make, and there's methods that we're trying to move towards that are more automated, more technologically adept, better use of the system we have, but it's going to require some cooperation. We have 5 transit systems in the Puget Sound region, if you don't count the ferry system and Kitsap Transit, so you could say we have 7. We have a highway department or transportation department that really does have to worry about the highways and bridges and has money that is spent in certain ways. Gas tax can only be spent for highways, cannot be spent on transit. And we have communities that are trying to connect their roadways, connect their bike paths, make them more walkable, make them more livable. And we have a lot of politics going on at the federal level. It's pretty obvious we're not going to see much action in transportation while we're arguing about healthcare and education and climate and everything else. So our state legislators are working really hard right now to figure out what the state's role is in transportation, not just highways, but transit. And how about bike paths? And what do we do about fish passage barriers? That we have a huge burden of an environmental issue around stormwater runoff. How do we take care of the systems that we have? A lot of burdens that they're discussing right now, and they're going to need your support as good engineers who have good solutions and know that a proper investment in our transportation system really is going to help our economy of our state go further. There's a lot of hope for new technology, and this is something that as we think about climate issues, extreme weather, adaptation, resiliency, all of the things we're trying to worry about, we're also trying to reduce emissions. We're trying to use technology that's coming forth from electric vehicles that, oh, by the way, don't pay any gas tax. So remember my gas tax story, that will become even more of an issue. We have the autonomous vehicle, the Google car, that if you think about what that might be, closer headways between cars, they'll take up less space on the freeway, maybe that's more throughput. What will that look like? Will that really happen in our lifetimes? The picture on the top with the circles is, in Ann Arbor, Michigan, is a test on connected vehicles. Vehicle-to-vehicle communication, vehicle-to-infrastructure communication. Can the car back from the traffic signal get the signal from the light that says it's about to change, and for safety purposes, slow down long before they see that red light? And can those cars, because they communicate between each other, which is testing out, so the technology is actually there and working, the vehicle manufacturers are working with US DOT and talking to them about what the regulations might look like, or the framework for the regulations, so that they all put the same kind of architecture inside the vehicle so that they do talk to each other. Will eliminate rear-end collisions, side swipes, lane change issues, all of those kinds of things are really exciting new adventures for the ability for cars and vehicles and roadways to be more safe and to work better. Now, the kinds of things that are in place today are the flow maps. The facts that smart highways don't just tell you what's happening up ahead on your corridor, but the more you know about what's going on other corridors helps you make decisions, help the system work better, and that kind of technology is readily available. So think back to that muddy road that the Model T was trying to slog through, and the fact that that was only 100 years ago. And it makes you wonder where we're headed. And Greg had his whiz-bang picture. I grabbed mine. This is not Elon Musk's Hyperloop. This was envisioned in 1930 on a powered bullet train. And to me, it just looks like the Alaskan Way tunnel in the air or something. But all of these concepts for where we're headed really are maybe old, maybe new. Maybe they're going to happen in this fashion. But when you think how far we've come from the early 1900s, you can see that there's limitless opportunities. It's going to take commitment, it's going to take vision, it's going to take cooperation. We could do with a little less politics on all of it, but with the goal of trying to move towards on a healthy economy for our state, healthy environment so that our quality of life is what we want it to be, and our communities are healthy and livable and the kinds of communities we want to live in. Those kinds of visions can help make anything possible in transportation. Thank you.